everyone, and welcome back to another video by the Ways Tutor. This is the fourth video of the larger functions and graphs topic. And today we're going to be going over inverse proportion and hyperbolas. We touched a little bit on hyperbolas in the previous video in powers and polynomials, but this is something we're going to focus on a bit more in this video and hash out what the sort of concept is. And how we deal with it mathematically. So, as an overview, the first thing I'm going to be looking at is examining the concept of an inverse proportion, what that actually means, as opposed to, for example, direct proportion. And once we've come to an understanding of what inverse proportion is, I'll be having a look at being able to graph inverse proportions and the more general hyperbola, and also being able to determine what the equation of a hyperbola is given the graph, which is a common theme that we've dealt with in a bunch of the functions topics that we've dealt with so far. So let's get straight into it. Okay, so the first thing I'm going to go over is the concept of inverse proportion. And essentially what an inverse proportion tells us is that one variable, we'll call that variable y, is proportional to 1 divided by another variable x. And what this tells us, and what this symbol says, is proportional to. And so if we say y is proportional to 1 over x, that means for every increase in y, there must be a subsequent decrease in x. And for every increase in x, there is a subsequent decrease in y. And this is what we mean by inversely proportional. They are directly inversely proportional in the sense that here, we can see this translates to y equals k over x. Okay, and so y and x are inversely proportional and they're linked by this constant here, k. Some common examples of inverse proportion are, for example, the number of workers you might have, and then the number of hours it takes to complete a job. And so if we let, for example, the number of workers be W and the number of hours to complete a job be H, then we know that W is going to be inversely proportional to H. And more specifically, we will have W is equal to K over H, where K is our linking constant, as before. And so if we, for example, say if we have 3 workers, it takes us 9 hours to complete a job. And then if we have we want to figure out how long it would take us if we have 4 workers, we would suspect that this number of hours to complete the job is going to be less. The important thing that we need to do to find the number of hours that would take 4 workers to do the job is by figuring out what our constant k is. And the way we can do that is substituting these values in. In this case, our 3 represents the number of workers, W, and our 9 represents the number of hours to do the job, H. And so as a result, we'll have 3 equals K over 9. And so as a result, K will be equal to 27. And so our workers is going to be equal to the number of workers and the number of hours to do the job. Our workers will be equal to 27 divided by H. And so as a result, if we consider 4 workers, we have 4 workers now, then the number of hours to complete the job, H, will be equal to 27 over 4. And this is the concept of inverse proportion here. It's something completely different and it should be distinguished from direct proportion, where direct proportion refers to a linear correlation between 2 variables. For example, y is proportional to x. And in this case, we have y equals kx, for example, where k similarly is a constant. And if we were to graph this y equals kx on a set of axes, we would see that we have a line passing through the origin, and it will have gradient k. So our gradient equals rise over run, and that will be equal to k. Okay? And so this is what direct proportion tells us. It should be distinguished from other lines or other linear relationships because in this case it's passing through the origin rather than through some random point of intersection here. And similarly, inverse proportion involves a 1-to-1, 1-to-1/1 relationship rather than some random constant. Some random constant that pops up here. Okay? And if we look at a graph of inverse proportion, we'll see that it looks something like this. Okay, in the case of the workers, for example. And generally when we're considering inverse proportion, we only really consider this side of things, the positive values, because of course, in the case of the workers and the hours, you can't have negative workers, and similarly, you can't have negative hours to have a job. So often in real life scenarios, when you're dealing with inverse proportion, you're only dealing with this first quadrant right here in the Cartesian plane. Okay. Now that we've introduced inverse proportion, let's move on to hyperbolas. So we introduced, for example, the inverse proportion of k on x, and the most basic inverse proportion you can have is y equals 1 divided by x. And the easiest way I find to graph hyperbolas is just by plugging values in. And so I can get my Cartesian set of axes. I'll make those axes like this with my ruler. And that's 90 degrees. And so we have our y-axis and we have our x-axis. And so if we consider the points on this graph, we can have our point x is 1, 1, and then we have our point here. We can have the point 2, and that corresponds to 1/2. The point 1/2, if we plug that in, 1 divided by 1/2 becomes 2. And so we get something like this. And as a result, we can form our hyperbola like this. And then if we're plugging in negative x values, we should see a similar sort of reflection in the line y equals negative x, something like this, and it'll look very similar to what we saw before. Oh. Okay. All right. And so we have the graph of a hyperbola in this way. All right. And so importantly, in this case, we have the constant being positive. If the constant is negative, it'll look something like this. And I'll leave it up to you to see why that's the case. If you plug in your x values and see what your y values spit out to be, you'll see that it corresponds to these two values here. Okay. All right. So another thing you should be noticing about these is that as x tends towards infinity, y is tending towards 0, and it's more importantly, it's tending towards 0 from the positive side, and as x tends towards 0 from the positive side, y is tending towards positive infinity. This is something we looked at previously. So if we have our x here, and we have x is tending towards positive infinity, that means we're doing 1 divided by positive infinity, which means y is going towards a really, really small positive number, and that's confirmed here. Okay? And similarly, if we have x tending towards 0 from the positive side, we have 1 divided by a really, really small number, and so y tends towards positive infinity. And if we then consider the other side of things, we can see that y is also tending towards 0, but from the negative side. And here, y is tending towards negative infinity as 0 tends towards, as x tends towards 0 from the negative side. Okay, so that I'll write here. If we have x tending towards 0 from the negative side, that means we'll have y tending towards negative infinity, because we have 1 divided by a really small negative number, giving us a really large negative number. And similarly, if we have x tending towards negative infinity, that means y will tend towards 0 from the negative side. Okay? And so these are corresponding to those points there. Okay, so as a result, this hyperbola is also defined by two asymptotes, namely the y equals 0 asymptote, which is this one, and the x equals 0 asymptote. Hyperbolas will never be equal to y equals 0, and x will never equal 0, because at 0, y is undefined. So, if we apply some transformations to this y equals 1 over x, we can consider y equals 1 over x take h plus k. All right? And here, in this case, we will have different asymptotes. The important thing here is that one asymptote will be the point x equal h, and the other asymptote will be y equals k. And if we consider what this equation, if we break down what this equation sort of looks like, we can see that if x equals h, then h minus h is 0, which is undefined. And similarly, as x tends towards positive or negative infinity, this will regardless tend towards a really, really large number or a really, really negative number. And so as a result, this will tend towards 0, leaving us with y approaching k from either the positive or negative side. And so as a result, if we graph our set of axes like this, and we graph it, and similarly we know that our coefficient here is positive, we'll have something like this, where this value here is our k, y equals k, and this bit here is our x equals h. And so as a result, we have something like this, and something like this. Okay? Now, the important things we are going to need to be able to graph. The easiest things to extract from any graph of a hyperbola are the asymptotes. That'll be this point here and this point here. Once we've done that, the other important points are the y-intercept and the x-intercept, giving us 1, 2, 3, 4 marks. And finally, the shape. So a hyperbola's question can be up to 5 marks. The easiest way to deal with hyperbolas is simply plugging in x values here and then seeing what y outputs. And that's also how we can determine specific variables in the case where this is, for example, k. Or not k in this case, let's make that a. Okay? If we want to find a and we know our h and our k and we know a single point on this graph, and let's say that's 3, 5, let's say that's a point, we can plug in our values 3 and 5, and as a result, we'll be able to find a. So let me take an example of how I would graph a hyperbola. I'll just make some space. So if we have a hyperbola that looks kind of like, let's say, y equals 2 over x take 4 plus 3. Now the key bits of information. I can see here that one of my asymptotes will be x equals 4, and the other asymptote will be x equals 3. Okay? The other thing I've noticed is that this value here is positive. And so as a result, if I graph this on a set of axes, I know it'll look something like this, rather than something like this. Okay? And so the first thing I want to do is I want to graph where my asymptotes are. Sorry, this should be a y equals 3. I want to graph my asymptotes, and I graph y equals 3 in this case, and x equals 4 up here. Okay? And now what I want to do, I know it's going to graph and look like something like this, but I also want to know what my intercepts are. So I know my y-intercept occurs when x equals 0. So I let this point here equal 0, and when x equals 0, I have y equals 2 over 0 minus 4 plus 3, and so y equals negative 1/2 plus 3, which is equal to negative 5/2. And so as a result, oh sorry, that should be 5/2, not negative 5/2. 5/2. And so as a result, I have my 5/2 that I've put right here. And I know that that's 1 point. And similarly, I want to find my y-intercept. And so my x-intercept, sorry. So I have 0 equals 2 over x minus 4 plus 3. So negative 3 x minus 4 equals 2. Negative 3x plus 12 equals 2. Negative 3x equals negative 10. So x equals 10 over 3. And I will just pop that point right here. And so I have this point here, and I want to maybe plug in some values. I'll plug in 5 to give me a nice whole number on the denominator, and that'll give me 5, 5, for example, 5 and 5, and I get this point here. And similarly then maybe I want to get to 6. 6 minus 4 is 2, so then that would give me from 6, I would go down to 4. And so I can plot a hyperbola based on this, and I can connect these 2 points up to make the hyperbola here. And so based on these pieces of information, I'll also be able to determine the formula of the hyperbola, and namely it'll be relatively straightforward given that we can see the asymptotes, so we know it'll look like y equals a over x minus 4 plus 3, and then the only thing we need to do is we need to plug in a value like this, 5 on 2, 0, 5 on 2, and so as a result we can get something like this, and so 15 on 2 equals negative a on 4, and so I've done something wrong here. Oh yeah, sorry. Negative 1/2 equals negative a on 4, so a in this case equals 2. And so in this way we've been able to find the equation of the hyperbola given the graph as well. Okay? So I have gone over that quite quickly. This is quite a short video, but let's just review and recap what we've learned. So I introduced the concept of inverse proportion, where a variable y is inversely proportional to x, can be written as this, and this is to say that y equals k over x. One such example is workers versus the number of hours it takes to do a job. So not job, hours for job. Okay, so that's one such example. And there'll be other examples in your Sadler textbook if you go have a look at those. We then had a look at the graphs of y equals 1 over x and the more general form. I also included a vertical translation. So that is the plus k bit that I included. And I'm not sure why they haven't included that in the syllabus, but that is part of the Year 11 Methods course. We also had a look at the hyperbolic shapes, what those looked like, and the asymptotes. Those are the easiest things that you're able to deduce from any equation and from any graph as well if you're trying to determine the equation. And so we've covered everything we need to know from the inverse proportion section. Just want to thank you guys for watching. Remember to comment if you have any questions regarding this content or if I've missed anything in the inverse proportion topic, and make sure that you're subscribing so you don't miss any new videos. The next video will be releasing on the 19th of October, so stay tuned for that.